In module 2.2, we are going to study the complex exponential. We had announced this sequence as being a fundamental character in our play, and it is time to meet it more in detail. It is not a completely simple object, but it has many features that will be useful later on in this class. In particular, there are periodic complex sequences that we are going to see, but there is also a notion of frequency, which is a discrete time frequency that is quite subtle. In continuous time, frequency is very natural. Think of frequency, for example, in music, in musical instruments, and so on. In discrete time, the notion is more subtle because there is an increasing frequency that after a while looks actually like a smaller frequency. And this phenomenon, which is well known if you watch old movies, when you have wagon wheels that turn backwards, even though the wagon is actually moving forward, is an effect called aliasing that we need to understand because it's very particular to discrete time signal processing. Then we will finish the module 2.2 by seeing the relationship between a discrete time frequency and an equivalent continuous time frequency, which is very important, for example, if you want to synthesize a sound from a computer into an acoustic system, or, of course, in the reverse, when you acquire a real-time signal from the continuous time domain and you want to create a sequence. The overview is the following. We are going to introduce a complex exponential, see periodicity, then a special effect which is called the wagon wheel effect, and the maximum speed of discrete complex exponentials. Then we are also going to contrast digital and real-world frequency notions. As we have said in the previous submodule, oscillations are everywhere. The cardiac beat, the whistle on the train, the waves on the ocean, the violin strings. The oscillation needs the following ingredients. First, we need a frequency. The unit will be radians. So we will always look at the unit circle, and the full circle is in radians 2 pi. There will be an initial phase phi in the same unit, of course, radians. There will be an amplitude. This amplitude will depend how we measure the physical phenomenon. And we therefore get a trigonometric function, which is the sequence, for example, xn, which is given by a, the amplitude, times the cosine of omega n plus phi. So the phase term phi, the frequency omega, the time index n. Okay? So this is the basic ingredient of a trigonometric sequence here that is going to be periodic and has an initial phase phi. Now, we always use complex exponentials. Now, some of you might not like complex numbers, but complex numbers are our friends here because they make trigonometry much simpler. So, a trigonometric function that is expressed as a complex exponential, of course, can be reduced to sines and cosines using Euler's formulas. Okay, so we have a sequence xn, just like previously. We have, let's say, a is the amplitude, e to the j omega n plus phi, and by Euler's formulas, this is the amplitude, cosine omega n plus phi, that's the real part, j times sinus omega n plus phi, which is the imaginary part, and together we have a complex exponential. So we see that sines and cosines always come together. And the reason why we prefer exponentials to sines and cosines is that the mathematics are simpler. Instead of doing trigonometry, we do algebra. And last but not least, we actually have complex numbers in all digital systems that we use. So on your computer, you have real numbers, but you have also complex numbers, and you can do complex arithmetic. Okay, so let's look at an example of the advantages of using complex exponentials. So you want to do the change of phase of a pure cosine. So you start with a cosine omega n plus phi. This will be written as a times cosine omega n plus b times sine of omega n, where a and b are given here. So if you know your trigonometry by heart, you know this is a very natural thing. But you know, if you don't remember all the trigonometric formulas, you can always look them up on Wikipedia, but it is a little bit a cumbersome way to actually deal with such simple operations. Okay, so instead, what we do is we look at the change of phase of a pure cosine by stating that the cosine is the real part of a complex exponential. The change of phase up here is an addition in the exponent, and the result is that we simply have a multiplication here in the complex exponential. So the phase that was up there, of course, by the fact that it's in the exponent, will end up just being a multiplication here by the phase. So the phase change is extremely simple in the complex exponential domain. At the end, we simply take the real part, we get the cosine, and we're all done. Okay? Notation is simpler. Phase shift is a simple multiplication. So these two effects are why we prefer complex exponentials. Okay, so what is a complex exponential? It is Euler's formula again. E to the j alpha is equal to cosine alpha plus j times sine alpha. Okay, I'm repeating myself, but it's such a beautiful formula that we can see it a couple of times. It won't hurt. Okay, so let's plot this in the complex plane. So the complex plane has a real axis and an imaginary axis. So e to the j alpha, given by cosine alpha plus j sine alpha, lives on a unit circle here. That is this nice little circle here. And the complex number e to the j alpha is, well, cosine of alpha, which would be here, plus j sine of alpha, which is here, and it is a vector of length 1 that reaches a unit circle and has an angle alpha here with the real axis. Okay? So, if you're not very familiar with this picture, please look at it, play with Euler's formula, go back and forth between real numbers and imaginary numbers and so on, because this is the alpha and omega of what we will be doing here in this class. Okay, so if we have a point on the complex plane, z, this location, and we want to rotate it, then the argument is that we can simply multiply it by a complex number here, e to the j alpha. That's the previous character, and it will exactly move z by an angle alpha. Okay? So rotation amounts to multiplying with a complex number which is of unit norm. So a complex number of the form e to the j alpha. So you can see that a relatively complicated operation on the complex plane, which is moving from here to z prime, is actually very simple in this algebra using complex exponentials. Let's look at what we will call the complex exponential generating machine. xn is equal to e to the j omega n. xn plus 1 is simply e to the j times xn. And so recursively we're going to generate successive samples of this discrete time complex exponential. So let's start at x0. It's straight on the real line. Then it will move by omega. That gives x1. By 2 omega is x2, etc. It will keep going x4, 5, 6, 7, and so on. And in this particular case, x12 happens to be back at the origin. And therefore, it will be a periodic, discrete, complex exponential. Now, if there is an initial phase, we don't start from the real line, but we'll start with an angle theta. But then the same story goes on, and as we go x6, 7, etc., at x12 we will be back at the same location as x0. Now, one has to be careful, because not every sinusoid is periodic in discrete time. And we have an example here where omega is chosen such that the result will actually not be periodic. So x1 moved by omega on the unit circle, x2, x3, 4, 5, 6, 7, 8 is not back to the origin, and we can keep going like this, and it's not hard to see that this will not be periodic. What does periodicity mean for a discrete time exponential? So e to the j omega n is periodic if and only if omega is equal to a rational factor of 2 pi. So m over n times 2 pi, where m and n are integers. And in this case, we can actually use the fact, of course, that if we add a multiple of 2 pi to the angle of a complex exponential, we are back to e to the j omega. The quiz is about if a signal e to the jn is periodic. On the complex plane, a single point can have many different names, and this uncertainty, in some sense, is one of the reasons why complex exponentials in discrete time are interesting but sometimes difficult objects to deal with. If I write the red dot here, e to the j alpha, I could have also said that it's actually the same, except that I had gone alpha plus 2 pi. Or I could have gone alpha plus 6 pi, or any multiple of 2 pi. I could also have said that the angle was actually a negative angle of alpha minus 2 pi, and this will give me the exact same point, e to the j alpha. So the question is, how fast can we go? And here we are going to watch a movie, and the movie is a depiction of this famous wagon wheel effect that you probably have seen watching Western movies, old Western movies on television. Let us do an experiment. Here we have the wheel of a bicycle. It has 4 spokes, so it has 4-fold symmetry, and between 2 frames we see it advances by the number of degrees shown at the upper left corner. So we see it goes faster and faster. Now, because of 4-fold symmetry, everything that we have seen before is complex exponentials will be divided by 4. So when we approach 45 degrees, we start to have the feeling the wheel goes backwards. At 45 it has a funny effect, and it starts to go backwards, and it will slow down. Again, the wheel has a 4-fold symmetry, so we are approaching 90 degrees when it will stop. 80, it gets slower and slower, even slower, and at 90, we're soon there, it will actually stop. So the wheel is actually turning. It turns by a quarter of the circle every frame, but of course, because of a 4-fold symmetry, it actually stops. Okay, that's an illustration of aliasing. To understand this, we are going to look at frequencies, and we increase the frequency. So the first frequency, omega, is equal to 2 pi over 12. So it is a very small frequency. It's a one we have seen before. So x0, x1, etc. turns around, and sure enough, x12 is back to the real line. If we take omega is equal to 2 pi over 6, so that's a much larger frequency here, but it's still a divisor of 2 pi, and so we have x1, 2, 3, 4, 5, and x6 is equal to x0. Again, a periodic signal. If we go up in frequency, omega is now equal to 2 pi over 5, it is a periodic signal, sure enough, but you can see that its frequency now is very fast. 2 pi over 4, we simply see the 4 quadrants here, x0, x1, x2, and x3. 2 pi over 3 divides nicely the unit circle into 3 pieces. 2 pi over 2 is equal to pi. That's an interesting signal because it simply alternates between +1 and -1. And it will alternate like this, and so this is the maximum frequency discrete time complex exponential. Now, if the frequency is between pi and 2 pi, then there is this illusion that we can either think of it as a positive frequency, slightly larger than pi, or a negative frequency, slightly smaller than pi. Now, when omega is equal to 2 pi minus alpha, and alpha is small, then of course we are going to most likely think that it's actually a negative frequency. So here we have an example of x1, which is 2 pi minus alpha away, but is also minus alpha from the real line. And if we do this, we see now that we have the sense of a negative frequency. Let's now think about the difference between digital and physical frequency. In discrete time, n has no physical dimension, it's just a counter. And periodicity is how many samples before the pattern repeats. In the real world, periodicity is how many seconds before the pattern repeats. And the frequency is measured in hertz, or second minus 1, which is 1 over the number of seconds until the pattern repeats. Now, if you have a PC that plays sound, you have to map digital frequency, or a discrete time signal xn, through a sound card into a loudspeaker. And so there has to be a relationship between the clock frequency on your computer that maps into a physical frequency out in the real world. This is given by the system clock. So the sound card has a clock, TS, and every TS second it will generate a sample that will be interpolated and fed to the loudspeaker. We can set the time TS between samples. So periodicity of m samples means a physical periodicity of m times t seconds. So the real world frequency is going to be f is equal to 1 over m times ts.